Welcome to Ask and Learn.
Okay, so with this problem, you basically have a gas that's compressed isobarically, then adiabatically has its volume increased, and then finally isochorically it goes back to its original state. And there's just some questions about the temperature and pressure along the way. So the first part asks just to draw a PV diagram. So, oh yeah, and then I already just wrote down some of the givens. So just like the number of moles, the initial pressure, initial temperature, and also the fact that it's nitrogen and it's a diatomic molecule. We know we need to use gamma is 1.4 for the heat capacity calculations. So I looked that up in a table in chapter 19, and I wrote it down. So anyway, so part A, our little PV diagram. So yeah, here's P, here is V. And after a little bit of trial and error, I realized, it starts in the right corner, top right corner. So decreases its volume to half. So this one we'll call V1, and this one we'll call V2, and we'll just say that V2 is V1 divided by 2. And then I'm going to label this state 1, so all my subscripts kind of make sense. Okay, anyway, and then finally it goes to state 2 when it's decreased its pressure. And then it adiabatically changes its volume back to the original. And so if you look at the book, you know that adiabatic curves on a PV diagram sort of had this shape. And then so that's state 3, and then finally it just like goes back to where it originally was. And I'll stick these little arrows so we don't forget which way. Okay, and part B, I'm just gonna like switch up the color so it's not a bunch of black. It asks for the temperature at two. And so basically you want to use PV is nRT. And so you want to say, algebraically manipulate this to say, well, P at 1 is equal to V over NR. Oh, you know what? Actually, that's not what I want to do. I do want to do PV as nRT. But with these, I like to start with just considering what stays the same. So the pressure stays the same. And so that's P equals nRT over V. So that stays the same. So then you can just kind of stick subscripts on here and then say, well, if it's this computation at 1, it's going to be this computation at 2, and then they have to be equal because the pressure stays equal. And then if you just cancel NR, because NR doesn't change, R is a constant, and then the number of moles doesn't change, then you just get this simple equation, T1 over V1 equals T2 over V2, and then you get that, oh, I want to keep writing in green. Then you got the T at 2 is equal to V at 2 divided by V at 1. Sorry, this is getting kind of sloppy. Times T1. And I will emphasize that's a 2. So yeah, I just like algebraically manipulated that. And then we know V at 2 divided by V at 1 is a half, because V at 2 is a half of V1. And T1 we know is 300. And so we're just going to half that to get the new temperature. I almost wrote 3. Okay. 150 Kelvin. And you know what? I'll just keep using different colors for each part. And then they also wanted it at 0.3. So to get that, you want to just use these equations that relate the different quantities for adiabatic processes. So the relevant one is T2 V2 to the gamma minus 1 equals T3 V3 to the gamma minus 1, and that's just from the book on adiabatic processes. And the answer really pops out just now it's just kind of doing the math. Some people struggle a little bit with the algebra and with these exponents. So I'm just going to go ahead and write out sort of how to do the algebra. So I'm going to just divide both sides by like v3 to the gamma minus 1. So then that's T2 V2 to the gamma minus 1 over V3 to the gamma minus 1. According to algebra, you can just kind of, stick that whole thing. It's the same thing as taking the ratio of V2 and V3 and then bringing it to the gamma minus 1. And we know V2 is half of V3. So then so you're just going to plug in a half here. And then for T2, I'm just going to use the 150 Kelvin from the first calculation. So then it's just going to be 150 times 0.5 to the gamma minus 1. Gamma is 1.4, so I can do gamma minus 1 in my head. That's just 150, or it's just 0.4. And then if you plug that into a calculator, maybe you'll get the same thing I got, which is 114 Kelvin. So I guess the adiabatic curves are a little bit lower than the oh my god, that word is slipping me. The one where the temperature stays the same. So yeah, interesting to note. Even though they kind of look pretty similar, I think, the adiabatic curve is going to sit a bit lower. Okay. So for part C, now I get to use blue. God, the word is slipping me. Iso temperature. Okay, well, I'm not going to worry about it. So here's C. The question asks for the pressure at 3. And again, we can just use our favorite adiabatic transformation equation. So if the transformation is adiabatic, then you get this relationship between the pressures and the volumes. So again, we have like everything we need. So we just need to algebraically manipulate the equation. So I'm just going to do it in the same exact way, except for a little faster. Oh, that looks bad. Okay. So then that's just V2 divided by V3 to the gamma. Our gamma is the 1.4. V2 over V3 is 0.5. And then P2 is the 1.8 10 to the 5. So if you plug that onto a calculator, hopefully you'll get what I got, which was 6.82 times 10 to the 4 pascals.